Hello, everyone. Today I'm excited to present our recent works on Instruct systematic improvement over DPSGD. So differential privacy is actually very semantic and intuitive privacy guarantee. So at a high level, differential privacy ensures that an adversary cannot easily infer the participations of individuals from the release. So to privatize an algorithm, basically there are 3 steps. First step, definitely we need to figure out what kind of processing functions we are handling on. It can be some simple statistical analysis like mean or median estimation, but it can also be more complicated like training a neural network. The second and also central questions in DP research is to determine the sensitivity. Right? So roughly speaking, sensitivity captures the worst case influence from an individual on the processing output. Only given the sensitivity, we can then properly determine like proper randomizations like to produce the required security parameters. Usually we will adopt some noise mechanisms, right? Okay, but unfortunately, sensitivity is intractable in many processing functions, and is actually NP hard to compute. So in practice, an alternative is decompose and then compose framework, right? So we will concentrate to decompose a complicated like a processing function into several simpler subroutines. So each of them may be like can be some mean estimation, where the sensitivity is controllable, and then we will assume a stronger adversary, like we will call it white box adversary, right? So instead of an adversary who can only observe like your final release, right? White box adversary will like observe all your intermediate iterates, right? And then we will add noise across those virtual release and use compositions. Like you can use RNE, DP, or FDP to compute the compositions to ensure a required like privacy guarantee. So actually, DPSGD is a classic example of this framework. Right, DPSGD basically is a workhorse for like privacy-preserving learning. It doesn't require any assumptions on either your training data or your training model, right? But unfortunately, we still don't know what exactly the sensitivity of SGD is, right? So we need to decompose the SGD, right? We view SGD as an adaptive gradient mean estimation, right? Every iteration, we will sample a subset of samples to calculate their pair sample gradient and aggregate them. Right, but here we cannot adopt the regular mean estimation or like the aggregation because there's no bounded sensitivity is ensured. So in practice, really we use clipped gradient. So clipping basically is an operation to project your input into a L2 norm ball, and then gives us a sensitivity upper bound in L2 norm. And then we virtually assume, okay, all the intermediate iterates is released, and then we really add some Gaussian noise, such that after T iterations, it can produce a epsilon delta guarantee. So the more intuitive part of the utility loss in DPSGD is caused by the noise, right? If it takes a longer time to converge, and also if you deploy a larger model, definitely you add more noise. But the other also important issue for the utility compromise is the clipping bias. As I mentioned, right, so clipping is actually an artificial sensitivity control. So actually in our paper, we actually prove in the worst case, clipped SGD even without DP noise will fail to converge if we only ensure your stochastic gradient is of bounded second moment. But under more restrictive assumptions, for example, if you assume your stochastic gradient is in a symmetric distribution, right, or in a light-weighted distribution, some near convergence rate unknown. So there is some gap there, right? So in the worst case, we know DPSGD due to this privacy concern, right? So it may not converge. But in the most ideal case, it may be possible to match the performance of regular SGD. So to give you more sense, like what exactly is the influence from the clipping in our practical deep learning task, right? So we just record the pair sample statistics, right? When we train RNN20 on CFR10 with both regular SGD and clipped SGD. So actually, you can see from these figures, like for a regular SGD, the norm of the gradient will converge into 0 more quickly. And but as a comparison, right? So for clipped SGD, there exists a large substantial of the gradients whose norm is quite large, right? So this basically means, right, there exists due to the clipping bias, there exist outliers, right? There always exists a large fraction of sample cannot fit your current model state. Moreover, you can also observe that the norm continue to increase. That basically means that the accumulated clipping bias, right, becomes larger and larger. So not surprising, like definitely regular SGD in general will enjoy a faster convergence rate. And moreover, we also want to mention, right, so we cannot simply view bias as some random noise. It can be averaged out across the iterations, right? So in this figure, when we even increase the number of epochs to 1,000, where like the model trained out by the regular SGD already overfitting, right? But there still exists a clear gap on the model trained out by the clipped SGD. So actually, in this paper, our conclusion and the results are very straightforward and intuitive. So in one sentence, right? So we just want to point out the clipping bias is actually controlled by the variance of the stochastic gradient. Right, so this is just like we show an example here for the normalized gradient, normalized SGD, and for more, we also present more involved analysis for the clipped SGD, right? So given this theory, it actually allows us to, we have a clear goal in the following, right? So it's like how can we reduce the variance of the pair sample gradient under the sensitivity control framework? Right, so in this paper, as a first step, right, we point out like 3 directions for this goal. Right? First, from the optimization level, right, what to clip is to ensure bounded sensitivity control. Right, so not necessarily we need to clip the pair sample gradient. Can we clip something else, right, to some more stable updates with lower variance? Also, we need to know that like, the gradient is determined by both your loss function and the model selected, and also your input data. Right? So for the model or the network architecture level, what kind of neural network fits DPSGD better? Also for data pre-processing, right? What kind of processing we may apply on our training data to enable it to produce more stable gradient. So let's first plot the inner momentum here. So momentum is actually very classic, like commonly used in deep learning and optimizations for variance reduction and acceleration, right? So in our context for bounded sensitivity, right? So we're considering the pair sample momentum, right? So instead of clipping the pair sample gradient, we will store the latest k iterates when we run DPSGD. And every time we will evaluate our pair sample gradients across these k previous iterates, right? And we compute the exponential average of them, right? So you can say when k equals 1, this just becomes the pair sample gradient. And inner momentums actually through this aggregation, it averages out a substantial fraction of sampling noise. Although, like you can say the pair sample gradient is because it's not independent, right? But it still cancels out a lot, and it produces a much sharpened convergence rate. The second issue I want to mention is like when we borrow the classic network into the private learning setup, usually we need to make some modifications to those networks. So one example is the batch norm layer. So batch norm layer is a very important layers in the when you like for random network, like a generative network. But the problem is with batch norm layer, right? Your input must be a batch of samples. But here we want to enable the pair sample gradient computation. So usually most pair works replace batch norm with group norm. But the problem the issue we want to emphasize here is classic network is the architecture is optimized for those batch normal layers. So when we do these modifications or like the replacement, right? So we need to carefully to think about, okay, what kind of network architecture can really fit, given like we need to compute the pair sample gradient and use those group normal layers. So we propose several tricks in our papers to carefully adjust the layer structures and the layer sequence. And details can be found in our paper, but here we just want to show, right, with these careful coordinations, right, so we propose use the same number of parameters, we significantly decrease the variance of the pair sample gradient with a much faster convergence rate and the boosted training performance. Third thing I want to mention is that actually to achieve the variance reduction, actually the most straightforward way arguably is the average, right? So imagine if we have a small amount of public data, can we use the public data to average out the sampling noise of the pair sample gradient, right? So the trivial solution is, okay, we just take the average of the public gradient and the private gradient. But this will cause a problem, right? Because we only have limited number of public data. It will cause a heavy overfitting, right? So in this paper, we propose batch clipping, right? So we still want to use small amount of public data, but we won't fully use those public data for the training. We only use the public feature to smooth the gradient computation, but the public label will not be defined in the loss function. So in this way, right, so we avoid the overfittings. Finally, what I want to mention, right, so even if we don't know, or we don't have the public data, so can we still, through this averaging, this, can we propose some way to average out this sampling noise, right? So our theory also can be used to verify a recently proposed empirical technique called self-augmentation. Right, self-augmentation basically means, okay, we can use random data augmentations to generate a bunch of virtual samples, and we evaluate the gradient on those virtual samples and average them and then clip. So here we just plot like this. After the data augmentation, the pair sample gradient, the variance also decrease and gets a boosted performance. So as a summary, so in this paper, basically we present some fundamental theories to transform the abstract clipping, like a clipping bias reduction in differential-private learning to more concrete variance reduction. And we show through several perspectives, like how can we, through optimization level, network level, data preprocessing level, how can we systematically to improve and instruct DP optimizations instead of searching for, like use some brute force to searching for like the optimal model and the optimal hyperparameters. So that is all I want to talk, and happy to take the questions.
Any questions?
Hello, I have one question.
Sure.
In your talk, you say actually you treat each iteration equally and then divide the privacy budget uniformly, right?
Yeah. Yes.
So
yeah.
is there any improvement you think we will have if we treat each iteration non-equally?
Good question. So actually, there are many empirical works to, for example, adaptively to adjust from the learning rate or like the clipping threshold, right? So if you think that iteration is more important, you can spend a larger clipping budget on that, right? But this is not our main focus of this paper. We want to give some more generic descriptions of the clipping bias, and from the effect from the noise side, this is not our main focus. We are more focused on the clipping bias side. But definitely, there are many empirical works you may want to check, like adaptive clipping or for the improvement.
Get it. Thank you.
Okay. Yeah. One more quick question.
Okay. Yeah. Thanks for the nice talk. My question is, given this approach that you use for the momentum and use the variance in the gradients, As I understand, some of the results in DPSGD's privacy analysis depend on this amplification via subsampling theorem. Now, if you do this momentum-based approach, are you not using users' data more often? And how does this relate to?
This won't change the subsampling amplification result because we use a single data to calculate its own momentum. You just can view that momentum as a special pair sample gradient. So all the privacy analysis won't change in our framework. We only focus on how can we use optimization tricks to improve that clicking bias. But the privacy analysis will be exactly the same compared to the DPSGD.
Okay, thank you.
Yeah.
Okay, let's thank the speaker again.